In this video lecture, we continue our discussion of sound waves. But first, let's recall what we used to know about waves on strings. I show a standing wave on a string, a three-loop standing wave, you could describe it, or a standing wave with three antinodes. It's called a standing wave not just because there are places along the length of the string that are not moving at all, or standing still. Those places are called nodes. But it's also called a standing wave because the wave is not traveling. It's stationary. All right, enough of that. The point I really wanted to make about this particular wave is the following. I show outlined in red here one full wavelength. It encompasses the following four segments of the wave from N, a node, to A, and then from A to N to A to N. 1, 2, 3 of those NA distances or AN distances, as you like. And so the four of them, each of equal length, add up to a full wavelength. And so one of these segments, one of those distances, symbolizes NA bar, has a length of lambda over 4. We'll use that fact as we return to our discussion of sound waves, beginning with a discussion of standing waves in tubes, also called resonances of sound in tubes. I show a speaker. The membrane is vibrating. It's sending sound into this tube, that end of which is open. The other end happens to be closed. Now, what I've diagrammed here is one possible resonance condition that can exist in this particular tube, and in all tubes that are open at one end, closed at the other. It's labeled A at the open end, N at the closed end. It's important for you to know the following. Wherever there is an antinode in a sound wave, the air molecules are doing this, vibrating back and forth at that location. That's the behavior at an antinode of a sound wave. It's analogous to the behavior at an antinode in a string wave. Let's walk back over here. And at this location where there's an antinode, the string is doing this, doing that, and frozen at places in between. So what we have here at the open end of this tube, which is an A or an antinode, the air is doing that. At the other end, where there's a barrier, the sound can't do the same thing as is done at the antinode place. The air at that point in the tube is frozen still. No oscillations whatsoever. This is one possible mode of vibration in this particular tube of this particular length. There are other nodes, or modes, I mean to say, of vibration, ways in which sound can resonate in such a tube. I show the next lowest frequency that will resonate, AN, AN. So the air there is doing that and doing that. There at the node, no movement, no movement. Now, we wish to determine what is the wavelength of the sound that can make, for example, this particular mode of vibration, mode of oscillation. We could do it for this one, but let's look at this one instead. We have this important rule here that the separation between a node and an antinode in any sort of wave, not just a sound wave, but string waves, has a length of lambda over 4. we have 1, 2, 3 such distances, each being a quarter lambda in length. The sum of those 3 distances, the sum of those 3 lengths, is the length of the tube. So we have 3 times a quarter lambda equals L. We can solve this equation for lambda if we wish, but we'll save that calculation for later. Once you have lambda calculated by using a procedure such as this, an equation like that, you put it there in the wave equation and solve for the frequency. But first you need to know what the speed of sound is. You weren't told what it is, perhaps in the previous video lecture. If so, I'll tell it to you again. To the nearest 10, it's 340. Actual value is 343, but we'll use 340 as our speed of sound. That's the speed sound has in air at sea level, at normal atmospheric pressure. Well, let's work a sample problem in which we calculate a couple of different resonant frequencies of a particular open-closed tube. My open-closed tube has a length of 0.85 meters. Our goal is to find the 2 lowest frequencies that will resonate. The 2 lowest frequencies will correspond to the 2 fewest number of letters that can label a tube. In this case, the fewest number of letters that will label an open-closed tube is A-N, 2 letters. The next fewest number of letters for an open-closed tube are 4 of them. And after that, well, I'll let you discover on your own. Let's look at the first resonance, A-N. There's one segment of distance A to N. That's the lambda over 4 segment, N to A to N, quarter lambda. So that distance there is a quarter lambda, but that distance is also the length of our tube. And so we see lambda is 4 times that number, which is 3.40 meters. Now we can use the wave equation to solve for F. F is the speed divided by lambda, 100 hertz. This lowest frequency for an open-closed tube, a tube of this length, one end of which is closed, is called the fundamental frequency. Sometimes we just say it's the fundamental. Another name for this lowest possible frequency that will resonate in such a tube is called the first harmonic. Since it's the first harmonic, why don't I subscript my frequency here as F1. It will be the first of a number of different frequencies that will resonate in this tube. We're only going to calculate the next lowest frequency. I'll leave it for you to think about, or calculate the other frequencies that will resonate. All right, let's calculate the next frequency. The next fewest letters that we can write down representing the nodes and antinodes is shown here. Notice that there are 1, 2, 3 of these A-N, A-N, N-A segments. So 3 times a quarter lambda equals the length of the tube. 4 times that is 3.4. Divide by 3. I'll leave it like this rather than decimalize that number. Now I use the wave equation shown here to find F. It's V divided by lambda. There's your V, there's your lambda. 3.4 into 340 gives 100. Flip the 3 upstairs. Final result, 300 hertz. Now, were we to do the next lowest frequency, the frequency that will resonate in that situation is 500 hertz, and then 700 hertz, and then 9, and then 11, and 13, and so on. So we find out, or you would see if you were to pursue this and find the next lowest frequency that resonates and the one after that, that all of the resonant frequencies can be summarized in the following way. They are all odd, keyword odd, integer multiples of the fundamental. The fundamental frequency is F1, 100 hertz. The next frequency, let us label it F3. Why 3 and not 2 for the second frequency? Well, 3 reminds us that this frequency is 3 times the fundamental frequency. If you were to do the next one, you'd find F5 is 500, F7 is 700, F9, 900 hertz. And so, to summarize, what we've discovered in our study of resonances in organ pipes or sound or in tubes, that one end is closed, the lowest possible frequency in a tube such as this is the one corresponding to this labeling, AN. In this example, 100 hertz. That's the fundamental frequency. It's also called the first harmonic frequency. The third harmonic frequency, F3, is 3 times the fundamental or 3 times the first harmonic frequency. Then there's the 5th and 7th and 9th harmonic frequencies. When I return next time, I'll look at the same exact tube of length 0.85 meters, but yet have both ends open. In such a case, you will find that the frequencies that will resonate in that tube that I will soon discuss are even integer multiples of, you guessed it, the fundamental frequency of 100 hertz. So expect to see that when the dust settles on that coming calculation, that the resonant frequencies in an open tube of this length are 200, 400, 600, 800, and so on.